Today we're going to solve shear and bending moment diagrams on this beam shown here. What we have is we have a roller support here and a pin support here, and then we have a 5 kilonewton meter applied load at the 1 meter from A mark. And the beam is a total of 3 meters long. So recall that a pin and a roller support cannot apply a moment. Therefore, the moment at these ends will be 0. So we're going to draw the free body diagram of the beam shown, then sketch the loading, shear, and moment diagrams. Okay? So the first thing we have to do, here I have my free body diagram, is we have to solve for unknown reactions. Okay? So what you do is you can either take the moment about A or the moment about B, and what that does is it eliminates the reaction, gives you an equation with one unknown, and then you can solve it. So I'm going to take the moments about A. Let's do this here. Sigma m A equals 0. And this is your positive direction. Okay? So you can see we have a 5 kilonewton meter applied load. Kilonewton dot meter applied load. And that, the other force applying a moment is the RB. So again, that's it, and this 5 kilonewton meters in a positive orientation. And then we're going to add, since this is also forcing the beam about A to rotate in a counterclockwise direction, we're going to add that RB times 1 plus 2 meters is 3 meters. And again, all this equals 0. So RB, 3 meters, equals 5 kilonewton dot meters, negative. So then RB equals negative 1.667 kilonewtons. And what that negative says is that my assumed direction is incorrect. It's actually going this way. Okay? So the next way to solve, now we have one unknown and one known. So what we can do now is we can just take the moment that sort of sum all the forces in the y direction, which is this way, and we're going to call this positive. Okay. So we're going to have, all of this equals 0 because it's a static situation. So we're going to have RA plus RB, but RB is negative, so it's going to be minus 1.667 kilonewtons. Remember, this negative indicates that it's actually going down, and all that equals 0. So then RA equals 1.667 kilonewtons. So we know RA and we know RB, and now we need to look at how making a shear and bending moment diagram. So let me just draw a line here. Okay. So what were the relationships that were important to solving these types of problems? Let's go back to the presentation. Okay, so we're going to do, we've got the change in m with respect to x is equal to v. Okay, so the change in m with respect to x, so dm by dx equals v, and there was one other one. The slope of the shear diagram is equal to the distributed load here. Okay, so the slope, dv by dx, equals the distributed load. So in this case, we have no distributed load. So this dy by dx is going to equal 0. So our shear and bending moment diagram should have a slope, our shear diagram should have a slope of 0. Okay, so these are the two relationships that are most important for solving these problems. So let's just take a slice right here. Okay? We're going to do method of sections. Okay. So this is going to be, actually let me just back up here for a second. Let's keep everything over here. So we're going to do this. Okay. So we're going to assume a shear. We're going to assume a moment. So this is V, and this is M. And we've got our RA here. Okay, so if we just look at this section right here, okay, we can just look at sigma Fy, so summing all the forces in y equals 0. Remember, this is up, positive. Okay, we're going to have Ra minus V equals 0, or Ra equals V equals 1.667. And since we have no other applied load, I shouldn't say we have no other applied load. We have an applied moment, but we have no transverse shear or anything like that. So that means our shear is constant all the way across. Let me just scroll through here. Where is it again? That means our shear all the way across is constant at 1.667. Okay, so let's just draw this. So we have our shear diagram here. And recall that when you slice this, when you look this way, a positive, a shear value, a shear orientation going down is actually positive. So this is going to be 1.667. Okay, and like I said, the applied moment here has no effect on the shear diagram. Okay, so that is our constant. So really, that's interesting, right? It means it's constant. So if you think about it, dm by dx is equal to v. So the change in m with respect to x is going to be equal to 1.667 across the entire beam. The trick now is we have an applied moment that's going to alter the beam, the shear and bending, the bending moment diagram. Okay, so now that we have this as shear, let me just write this as shear, and we'll do kilonewtons here. Okay. So let's just look now at our shear and bending, our bending moment diagram. Okay, so we're going to draw our diagram here. This is going to be m in kilonewton dot meters. I go across here to here. And by this relationship right here, we know the slope is constant all the way across. But what's going to happen? So it's going to start here, since the moment at a pinned end here has got to be 0, and it's got to be 0 here because it's a pin and roller. Recall that this here is a pin, sorry, this is a pin, and this is a roller. Okay. So we're going to have a slope of 1.667 this way. Okay, now that's going to have to change at an applied load. So whenever you have an applied load, as I talked about in class, you need to solve for it by section because you're going to get these discontinuities when this load comes into effect. So up to 1 meter, we're going to have a slope of 1.667. So we go up to 1 meter here. Let's call this your 1 meter point. And what is it? Is it, they labeled it? They haven't labeled it. So it's at the applied. So we've got A and B, and then we got a 5 kilonewton applied load. So dm by dx is equal to v times, so 1.667 times 1 meter. This is going to go up to 1.667 kilonewton dot meter. Okay. Now what happens when you have this applied load? You're going to get a discontinuity, but is it going to cause the moment to go up or the moment to go down? So let's think about this again for a second. So we're going to have, draw an FBD here again. We're going to have our RA, which is 1.667. We solve for our shear. We're going to have this moment here. Okay, so up to the point of the applied kilonewton meter load, or 5 kilonewton meter load, we're just going to have m is just going to be equal to, if you think about it for a second, and I might be mixing analytical solutions versus graphical solutions. But think about this for a second. If this is x, and you see I have an applied moment here, and this is positive, okay, m, about this point right here, m minus RAX equals 0, or m is equal to RAX, which is equal to 1.667 kilonewton meter x, which is what we have here. But once we hit the applied moment, let's draw another free body diagram here, and now we're going to have the applied moment. Okay, so it's going to be right here, and let me just double check its orientation. It's going to be like this. This is 5 kilonewton dot meter. So we've got an m here, and we have our shear. We're not going to worry about shear, but we're going to have this x value here. Okay, let me just clean that up. So now we're going to look at the moment about here, right? So sigma m equals 0 equals this m plus this applied kilonewton meter load, so 5 kilonewton dot meter, minus, remember your RAX right here, sorry, RA, minus, it's trying to push this way, which is clockwise, minus RA dot x equals 0. So your m is equal to RAX minus 5 kilonewton dot meter. So what happens when you hit right here is you now drop 5 kilonewton meters for that applied load. And then you go back up with the same slope. So as you can see, no rules have been broken here in terms of this slope is 1.667 kilonewton per meter, which, if you think about it, 2 times that will give you, it'll all add up to 5. If you take 3 times 1.667, you will get 5, which is basically, this is the distance here. This right here is your 5 kilonewton meter drop. So how did I know it was negative? One, you can do it by analytically here. But if you just think about it for a second, if I have this free body diagram here, let me just draw it again. Okay, and right here I have the applied 5 kilonewton meter load. Once I hit that, as I come along here, and this is x, once I hit this, in order to counteract it in a static situation, I have to apply a moment this way, right? To counteract that, because it's static, right? Remember, nothing is moving here. So that tells you that there's a 5 kilonewton meter drop. Once I hit it, in order for static situation to be true, if you have a suddenly applied 5 kilonewton meter load, then you need to apply a negative 5 kilonewton moment load to undo that. And remember, if we go back to our presentation here, the smiley beam is positive. Remember this orientation right here? Smiley beam is positive. Frown beam is negative, is what I said in class, right? So in this situation here, once I have this a 5 kilonewton meter applied load, once I get to this, just beyond it, I have to apply a negative frowning moment to make sure it's in a static situation. And that is ultimately what you get here, is this shows you analytically, which I just showed you graphically also, is that you have to get this 5 kilonewton meter drop here once you have that applied load. So as per our governing relationships for shear and bending moment diagrams, this hasn't been violated. dV by dx equals W, distributed load. So in this case, our slope is 0. Right? There's no change. There's no distributed load, so the change in my shear is 0. This slope is 0. dm by dv equals, dm by dx equals v, sorry. Well, this is 1.667. So I've got 1.667 up to here. I get my 5 kilonewton meter applied load, which makes this now your moment negative. And then we continue on at 1.667. So these relationships are maintained, which results in these two shear and bending moment diagrams. And recall that moments have no effect on sudden changes on a shear diagram, only point loads, and the same vice versa. If you have a point load, that's not gonna cause some kind of discontinuity here in your moment diagram. So I encourage you to watch this at your own pace again if you have to, and I'll try to post more videos as I can. All right.